So we are going to talk about angular momentum. Kind of already derived it a little bit earlier, and so we had said that if you've got something here and it's going around, you've got some momentum P because it's moving with some velocity V, okay, at R, okay, and so we would look at that and say, well, let's look about the angular part here, because we know that the force is dp dt, okay, and so by analogy, then torque would be the rate of change of something. We'll just give it an L right here, or your book actually uses a lowercase l, okay, and so it'd be a derivative of that. So what would that be? Well, to get torque, we have R cross F. So R cross F would be torque, so we R cross that. Okay. Well, R cross dp dt. So that is going to be the dl dt. So what is R cross dp dt? Okay, well, let's look at this. So if we have R cross P and we take the derivative of that, what would that be? That would be dr dt cross P plus R cross dp dt. Well, that would be V cross P plus R cross dp dt. Now, what is V cross P? Well, momentum is in the direction of the velocity, so anything crossed with anything in the same direction is zero. So that means that these two things are really the same thing. So that would mean that this is L. So L is R cross P. Okay. So if L is R cross P, that gives us a measure of angular velocity, angular momentum. Well, P is mv, so this would be R cross mv. Okay, and so that would be R cross, well, V. Now we start getting into the problems here with problems with the vectors, okay, and definitions, because we know that V equals R omega, okay, but the direction of V is not the same as the direction of omega, okay, because omega is perpendicular to how the motion actually is, okay. So this would mean, though, that R and V, L is perpendicular. So L is going to be in the same direction as omega right here. And so the angular velocity is going to be the same direction as omega. And so the magnitude of it, L magnitude of this is going to be R times mv. Well, V equals R omega, so that means this would be m r squared omega, or other words, I omega. So the magnitude of L is I omega. So again, we said that P equals mv, and wherever there was a P, we now have an L. Wherever there was an M, we have an I. Wherever there was a V, we have an omega. And so we can now that L, the angular momentum, is I omega, and it's going to be in the same direction as omega. So this is one way of writing angular momentum. Another way of writing angular momentum is R cross P. Okay, so both of these really mean the same thing. And so we have two different ways of introducing angular momentum. Okay. And the thing here about angular momentum that's really interesting is that the way you get angular momentum, okay, torque equals, the derivative here, okay, so for every force, there's an equal and opposite force. And again, we know that impulse is basically the change in momentum. So impulse, remember impulse from before, impulse was going to be basically force times time, and so that was the change in momentum. So torque times time will be the change in angular momentum. Okay. And so this would be, again, analogous to some of the things that we've seen before. Okay. So but because because torque has forces, then for every, remember, in order to get a torque, we have to have a force. So we have to have a force pulling on something in order to try to make it move. Now again, if R is this way and the force is up like that, then right-hand rule, that would say that the torque vector is coming out of the screen at you. And so that's, again, for every force, there's an equal and opposite force. Therefore, for every torque, there's an equal and opposite torque. And this is a problem. For example, you've got an astronaut floating in space here, and they've got a wrench here, and they're trying to turn a bolt. So when they try to turn the bolt, then it turns the astronaut in the other direction. And so it makes it very difficult to actually do anything with tools in space. Same thing with divers underwater. It's very difficult to use tools underwater because of the same effect. That for every torque, there's an equal and opposite torque. And if you're just floating, you tend to move around. Same thing happens here ordinarily, but normally you have friction that holds you in place, and that's not necessarily the truth in space or as a diver underwater. And so that's, again, applications here of this torque. Okay, but that means that just as before, we had said that initial momentum equals final momentum because for every force an equal and opposite force. Therefore, if one thing gains momentum, something else loses it. For every torque, there's an equal and opposite torque. Therefore, if one thing gains angular momentum, something else loses angular momentum. Okay, and so initial angular momentum has to equal final angular momentum. And so now we have an idea of conservation of angular momentum.